Hi all, this video is about replacement of capital items considering time value of money. In the previous video we had seen one problem in which we had the running costs, the scrap values, but we did not consider time value of money. Now in this problem we would also take into consideration the time value of money. So you could probably take down this question. You could pause the video and maybe take down this question for your reference, and we will go ahead from there. So you see there's a cost of a new machine which is mentioned as 5,000. The running costs of every year is given by an equation which is Rn is equal to 500 into n minus 1, where n represents the number of years possibly, just 1, 2, 3 and so on. And we have this money worth being mentioned as 5%. Now this we could in the practical sense take it as the cost of index or the rate of interest or the depreciating value of money each year, or you could even take it as the inflation index. So it's typically the price that you pay for borrowing a capital. So in that sense I think calling it the rate of interest may carry a little more meaning. As simple as if I say the money is worth 10% every year, and if I borrow 100 rupees this year, when I return it the next year I should pay back 110 rupees, because what I might be able to buy with 100 rupees this year might cost me 110 rupees next year. Therefore, the lender does not want to lose his purchasing power. So the lender might say, okay, you take 100 rupees this year, but give me back 110, because what you can do with 100 rupees this year, I can do it only with 110 rupees next year. So that's the value of money going down each year and your purchasing power going down. In order to take that into account, we have this considering time value of money. So if I spend 4,000 this year, it is 4,000. But if I spend the same 4,000 next year, it's actually a little lesser than 4,000. That is given by this percentage, and this percentage in this problem is 5,000 per year. Now I guess you must have taken down this problem now, and when we use this rate of interest in considering time value of money, we will use this formula, which is called the formula for discount factor. You could probably take this down, and while writing it, this is written as discount factor is equal to 1 divided by 1 plus r by 100. The entire denominator is raised to the power of n. This resembles the compound interest formula. I'll repeat, the discount factor is equal to 1 divided by 1 plus r by 100, and the entire denominator is raised to the power of n, where r is the rate at which money value decreases and n is the year. Now there's just a couple of observations that I just thought we should have a look. In our problems we have the running costs and we have the scrap value or the salvage costs that come up. When we use this formula of discount factor on the running costs, the formula should read as 1 divided by 1 plus r by 100 to the power of n minus 1. Be a little careful. The entire denominator is raised to the power of n minus 1 if we are using discount factor on the running cost. And if we are using the discount factor on the salvage value, then the denominator is raised to the power of n. The logic behind this is, if I raise the denominator to the power of n minus 1, and if the first year value n is equal to 1, then what happens is the discount factor is 1 divided by the term 1 plus r by 100 to the power of 1 minus 1, which is 0. So anything raised to the power of 0 is 1, and therefore the discount factor is 1, which means if I spend 4,000 rupees on maintenance cost in the first year, it is accounted as 4,000 rupees in the first year. That's because maintenance cost is deemed to have been incurred at the beginning of the financial year. But in the case of salvage value or the scrap value, when I use the formula discount factor equal to 1 divided by 1 plus r by 100 to the power of n, then let's say the salvage value of a machine which is 10,000 rupees, and if the salvage value at the end of the first year is 8,000 rupees, and this 8,000 rupees that I'm mentioning is the not discounted cost or the non-discounted cost. So it's presumed that the sale of the machine is accounted at the end of the year. Therefore, when I use a discount factor where the denominator is raised to the power of n, so let's say the R value is 10%, then possibly it will be 1 divided by 1 plus R by 100 to the power of 1. Now that would be, if R is 10%, 1 divided by 1.1, and therefore the discount factor would somewhere be around 0.9091 or something. Now which means at the end of the first year, if the salvage value is 8,000 rupees, and if I discount it by this factor of 0.90, then the value that I'm actually realizing at the end of the first year on the salvage is 7,200, about a 10% drop. So about 7,200 is what really I salvage, although on record it is 8,000 rupees. So we need to remember that salvage value is always accounted at the end of the year, while maintenance or running costs are accounted at the beginning of the year. And that's the reason when we use discount factor on running costs, it is n minus 1 in the denominator, and the discount factor for the salvage value would be n in the denominator. So the same formula, whether we use n minus 1 or n, depends upon whether we are applying it on the running cost or on the salvage cost. Remember, on the running cost it is n minus 1, and on the salvage cost it is n. Now we get into this problem that we had just taken down. So this problem said it's a 5% discount per year, which means if I apply the discount factor at the end of the first year, it should be 0.9523. Okay, so which is 1 divided by 1.05 to the power of n minus 1. Okay, this is not actually for the first year, but this is more of the second year. So 1 divided by 1 plus 5 by 100 to the power of n is 2. So at the end of the second year, the discount factor is 0.9523. So in the first year it would have been 1, because n value would have been 1 here. So 1 divided by 1 plus 5 by 100 to the power of 1 minus 1 would have been 0 here. So the entire term would have been 1 in the denominator. So 1 divided by 1, the discount factor at the end of the first year would have been 1. But the discount factor at the end of the second year, where n is replaced by 2 here, so it is 2 minus 1, 1 here. So it is 1 divided by 1.05. The discount factor is 0.9523 at the end of the second year in this particular problem. Now we need to prepare our columns like this. So have a look at this column. We have the year, the running cost, the discount factor, the discounted running cost multiplied by the discount factor. Then we have the cumulative discounted running cost. Then we have the capital cost plus cumulative discounted running cost. Then we have the cumulative discount factor and the average cost. Now we have to be a little careful here. In the first problem, when we did not consider time value of money, the average cost was divided by the year. But in problems where we consider time value of money, please remember that we have to divide the total cost divided by the cumulative discount factor. The total cost is not divided by the year. So please remember, in problems which are relating to the capital items we placed and considering the time value of money, then it must be that you divide the total cost by the cumulative discount factor. Please bear this in mind. So we have 8 columns in all. Now this is what we have here. What I will do is I will start deleting the table values. So we'll start computing them, or you would start computing them, and then we could always cross check the table values. Okay, till this we have the data, the year, running cost, discount factor we need to compute. Discounted running cost is actually the discount factor multiplied by the running cost, or that we multiply the running cost by the discount factor, corresponding discount factor. Cumulative discount factor, discounted running cost rather, cumulative discounted running cost is just the same way. In the first problem we tried to add up the previous year's maintenance cost to the running cost to the next year's, and consequently we had the cumulative cost going up together. And here it is capital cost plus the cumulative discounted running cost, these two, this column plus the capital cost and all. Then we have the cumulative discount factor. Just like we keep accumulating the running cost, we keep accumulating the discount factor also. And then the average cost, which is the total cost, which is column 6 divided by column 7, which is the cumulative discounted running factor. Now how did we get the running cost? That is again based on this equation. Very simple. The running cost is given by Rn is equal to 500 into n minus 1. In the first year, n is equal to 1. So 1 minus 1, this is 0. Rn is equal to 500 into 0, 0. So the running cost for the first year is 0. For the second year, n is equal to 2. So 2 minus 1, the running cost is 500. The third year, the running cost would be 1000. The fourth year, the running cost would be 1500. And the fifth year, the running cost would be 2000. And this is how we had computed the running cost, and that's shown here in this table. Now for calculating the discount factor, we have the same formula here that I had shown you, but the only difference is we use n minus 1 because we are going to work on the running costs and not on. Now I told you the discount factor we are going to use 1 by 1 plus r by 100 to the power of n minus 1, and in this n minus 1, n is the year. So if we use that, first year n is 1, so the entire denominator will be 1. 1 by 1, the discount factor for the first year is 1. If I calculate for the second year, this I had already spoken to you a little earlier in the same video. The second year's discount factor is 0.9523 and so on. Now if you keep calculating the discount factor, you should be getting this column. This should be 1.9523 and so on. Now let me get this column for you. Okay, so here we have the discount factors calculated. The next column is a little easy. You just multiply the running cost with the discount factor. So this should be 0. This should be 500 into 0.9523, 1000 into 0.9061, 1500 into 0.8636, 2000 into 0.8224, 2500 into 0.7832, and so on. If you do that, you should be getting these values here. And then the next column is a cumulative discounted running cost. So here it would be 0. 0 plus 476.15 should be entered here. And 476.15 plus 906.9, and so on. So you get this. Then we have the capital cost plus the cumulative discounted running cost values here. So the capital cost is 5,000. 5,000 plus 0 here, it should be 5,000. Then 5,000 plus 4765, 476.15. 5,000 plus 1383.05, so that should be 6383.05, and so on. That's the capital cost plus the cumulative discounted running cost values in this table. So this is what we have here, and then the cumulative discount factor. So this column 3 is the discount factor. So the cumulative discount factors will be, here it's 1, then the second row it is 1 plus 0.9523, so it's 1.9523. Then it's 1.9523 plus 0.9069 should be entered here, and so on. If you do that, you get your cumulative discount factor values here. And the last column is column 6 divided by column 7. The total cost, which is column 6, which includes the capital cost plus the cumulative discounted running costs, divided by the cumulative discount factor. So if you fill these values, it should be 5,000 by 1, 5476.15 divided by 1.9523, 6383.05 divided by 2.8592, and so on. Do this, and then we have these values here. So these are our average costs, and like in the previous problem, we keep examining whether the costs are decreasing. Yes, they are. The average cost is coming down to the end of the 5th year and begins to increase at the beginning of the 6th year. So the decision would be to replace the machine at the end of the 5th year. So here we go. This is a problem which took care of the replacement of the machine, of a capital machine, but considering time value of money. So as I always keep telling you, keep trying out more than one problem for every one problem that we try to solve in class or with assistance. So happy solving. Bye bye for now. Signing off as Jay.